Hello and welcome to another session of the Digital WE Days. My name is Ton and I will moderate this webinar today. The topic of today is RF inductors in high frequency design, selection, trends and challenges. Our speaker today is Anhuba Dixit. Anhuba, hello, cool to have you here. She will host the presentation and then she will answer your questions. RF inductors are critical for high frequency performance. But which technology fits your application best? Let's compare and optimize. Stage is yours, Anhuba.
Thank you, Sila. Thank you so much. So, hello everyone. As Silas mentioned, I am Anhuba Dixit. I work in the product management at iSource Group. Today, in this session, I will talk about RF inductors in high frequency design, their selection, the trends in the industry, and how the engineers cope up with the challenges that comes with the trends. So let's dive into it. Let me start with a quick question. Have you ever wondered how your mobile phone, your Wi-Fi, and even the radio in the car, every time they get the right signal, even though there are thousands of other signals in the air, right? So behind this magic are the tiny inductors that are playing their role in the background. So from 5G smartphones to IoT sensors, inductors silently shape the signal that connect our world. So now, these inductors are very critical in high-frequency circuits in wireless, IoT, 5G, 6G, GPS, and radar. Their performance directly impacts the system efficiency and signal integrity. Market trends show the growing demand for miniaturized, high-quality factor inductors. But these trends come up with key challenges like balancing the size, cost, and performance all together. Now, the agenda for today is, we'll start with the fundamentals. What is an inductor? How does it work? What makes RF field special, or what happens at high frequencies? The key selection parameters that designers must consider while choosing an inductor. Next, we will see what we have at worth in the RF inductor portfolio. Then, we'll talk about the emerging trends and the challenges that comes out with each and every trend. Then I will wrap up my presentation with the conclusion and key takeaways. So, let's start with it. Let's go back to the physics class for a minute and we'll see what is an inductor, how does it work. We all know that inductor is a passive two-terminal electrical component that stores energy in the magnetic field whenever electric current flows through it. When I say passive, it means that it can only absorb or store energy. It cannot generate the energy like an IC or a transistor. Now, an inductor is built by winding a wire around a core material. Now, this core material is not just a placeholder, it's a very specific design choice. We will see how it influences the inductor choice depending on our application. Now, the key working principle is classic electromagnetism, that when a current flows through a wire, it generates magnetic field around it. Now, by coiling this wire, we do two things. First, we concentrate the magnetic field around the wire in the center of the coil. Now, we have this magnetic field concentrated and strengthened at one place. This stored magnetic field is the source of inductor's properties. Now, when I say RF inductor, does it make any difference from power inductor? How is it different? Well, an RF inductor also follows the same physics, the same basic physics. However, when we move towards the higher frequencies or say radio frequencies, some hidden properties become dominant and the design priorities shift completely. So if I say that inductance is just the beginning story for high frequency design, that would be absolutely correct. And how is that correct, we will see in a while. Now, what makes RF field so special? Is it actually special? Well, RF field is not special because of physics. It follows the same Maxwell's equation, but it is special because how those laws of physics behave at higher frequencies. Now, when we talk about RF frequencies, which frequency range are we exactly talking about? So, according to International Telecommunication Union, the frequency range starting from 3 kHz and going up to 300 GHz is considered as RF. So when I say 300 GHz, I'm talking about a wavelength of 1 millimeters. So with those small wavelengths, such high frequencies, what's actually changing? First, the wavelength becomes very comparable to the circuit dimensions. So in DC circuits, the current and voltage are constant across the conductor. When we talk about low frequency AC circuits, the wavelength is so huge, maybe thousands of kilometers, if we compare to our circuit dimension, that the entire wire sees the same voltage and current at any instant. So that means it is location independent. But as we move towards the higher frequencies, this wavelength becomes comparable to the physical length of wires, PCB traces, or transmission lines. So the voltage and current vary with position due to wave propagation and reflections. Therefore, the size of cables, circuit boards, and even the components can no longer be ignored. Second thing, the parasitic effects start dominating the circuit. Now, these parasitic effects are the unwanted stray properties of the real-world component like inductor or capacitor that are not part of its intended function, but they're always present. At low frequencies, their effects are negligible, but as we move towards the high frequencies, they start dominating the circuit. So while designing a high frequency circuit, one of the main requirements is to minimize these parasitic effects. Third, the skin effect also comes into play at high frequencies. At DC, current flows uniformly through the entire cross-section of the wire. But at RF, alternating current, the AC current, is pushed towards the outer skin of the conductor. This effectively reduces the cross-sectional area. If we see here in the figure, this area of the conductor is reduced and all the electric current is flowing at the cross-section of this wire, which results in increasing the AC resistance. And as a consequence, conductors have higher losses at RF than their DC resistance would suggest. Now, let's look at the key parameters that we should consider while choosing an RF inductor. First, the inductance value. It's the basic thing, but choosing an inductor is not like we pick a 10 nanohenry inductor from the catalog. We should also consider the self-resonant frequency, quality factor, DC resistance, current rating, and last but not the least, size and integration. Let's see all these parameters in detail and learn how they influence our circuit design. First comes the inductance. So inductance is the primary characteristics we look for, just like for a resistor for a resistance in a resistor. Now, this value of inductance does not act like a simple resistance. Its opposition to current, called reactance, is directly influenced by the frequency. So this reactance is directly proportional to frequency. That means if we are increasing the frequency, the reactance is increasing. And also with this increasing reactance, the signal passing through it is it's blocked more and more by this inductor. Therefore, we should choose this inductance value very carefully for filters, tuning networks, and impedance matching circuits. Now let's talk about one of the most critical specs for RF inductor selection, that is the self-resonant frequency. The self-resonant frequency is the frequency at which the inductor naturally stops behaving like an inductor and starts acting like a capacitor due to its internal parasitic capacitance. We all know that when inductor and capacitance are placed in parallel, they form a tank network. And this tank network have their own resonance frequency. This resonance frequency is called self-resonant frequency. How does it come in an inductor? When we are talking about inductor, we say it's a wire wound. Then between each of these windings, there exists small capacitance, which is the distributed capacitance, stray capacitance, that we never intended to have, but it exists at high frequencies. And at one point, this capacitance became such dominant that our inductor stops behaving like an inductor and moved to a capacitive region. Now, this is a disaster for any RF design. For example, if I want to use an inductor in filter to block a high frequency noise signal, just say, but that signal is higher than the SRF, then what will happen? My inductor will pass that noise signal because it will act as a capacitor above SRF, and my filter will fail miserably. So choosing self-resonant frequency is very, very important criteria for inductor selection. And the golden rule in RF design is always and always select inductor with SRF which is a decade higher than the operating frequency. Now, let's talk about the figure of merit that defines the quality or efficiency of an RF inductor, that is the quality factor. It's the measure of efficiency in storing energy relative to its losses. This is absolutely crucial for performance. In a filter, high Q gives us a sharp, narrow bandwidth, which helps us to select a precise frequency and reject all the others. And if we talk about a matching network, what does high Q help us in there? So choosing a high Q minimizes the insertion losses, making sure that our precious RF power is transmitted to the antenna and not getting lost while heating up in between. Now, this Q factor increases with frequency. But at one point, for example, if we say here, the Q factor increases with frequency, but at one point it starts dropping. Why does it happen? Because when we go towards higher frequencies, more losses comes into play, and the skin effect also comes into play, leading to leading to more and more losses and reduction in the quality factor. Now, the peak quality factor often occurs before the self-resonant frequency. The other factors are DC resistance and current rating. DC resistance is straightforward. It's inherent resistance of the wire, which is used to build the inductor. A lower DCR means less energy is wasted. That means lower the power loss, higher the efficiency. We can simply translate it like a longer battery life for our mobile phone if we have the higher efficiency. Okay, and then we move towards the current rating. We might say that current rating is only for power inductors, but that is not the case. In RF design also, it's an important criteria. The maximum current an inductor can handle without saturation is called its current rating. When the core saturates, the inductance value drops dramatically. Consider it's like a tire of your car. If you inflate it more than what it's specified, it may burst at one point. It's the same for inductors. Now, let's break down the three main types of RF inductors, as each one of these have a very specific role to play based on their construction. First comes the wire wound inductors. These are the classic workhorses. We have a core, we have a wire, we wound the wire around the core. That's how we have our wire wound inductors. Now, these ceramic or ferrite core inductors achieve a very high quality factor. It makes them extremely efficient. But this efficiency comes at a cost, comes at a higher cost. Now, the second part is the multilayer inductors. Multilayer inductors, they are the champions of miniaturization and cost. They are made by printing a spiral pattern of conductor inside the layers of ceramic materials. This makes them incredibly compact, and they are perfect for mass product device like smartphones. But they comes at a cost of lower Q factor, because as physics say, as we go down in the size, we have to compromise with the quality of the inductor. Then comes the thin film inductor. Thin film inductors are fabricated by thin film inductors are also very compact in size, and we can say that they are the highest efficiency inductors. Now let's take a look at the inductors that Wood offers in their portfolio of RF inductors. First comes the wire wound inductors, wire wound ceramic inductors, which is WEKI and WEKI-HC. Then the wire wound ferrite inductors, WE-RFI and WE-RFH. Then comes multilayer ceramic inductors, WE-MK, and TCI, the thin film chip inductor. Then we have the air coil inductors and high current air coil inductors, WEAC-HC. Now we'll see the basic qualities of all these inductors and how they differ from each other. First comes the wire wound ceramic inductors, WEKI. It is formed by winding copper wire in a spiral shape around a ceramic core. The main properties is it has gold-plated contacts, high quality factor, high SRF, low RDC, and can support large currents. It comes with a tighter tolerance of 2% and 5% and are available in many different sizes from 0402 to 1008. Now, the ceramic core inductors are widely used in RF and microwave circuits due to their high quality factor, stability, and low losses. The ceramic core is frequency, temperature, and current independent. Because it's a ceramic core, so no magnetic properties, no saturation effect occurs, very low permeability, and minimal core losses we can see in this. Now we have WEKI-HC, which is a high current wire wound ceramic inductors. This is WEKI, but with thicker wire and thinner core. So I can say improved characteristics of WEKI. It has the same properties, high quality factor, high SRF, very low RDC, very large current they can support. They come with a tolerance of 2% and are available in two sizes of 402 and 0603. These are ideal for high current application, matching application in antennas, matching application in PA circuits. Then comes wire wound ferrite inductors, WE-RFI. It is formed by winding copper wire in a spiral shape around a ferrite core. Now, higher inductance in small size, but with core losses at high frequency, because we are talking about a ferrite core here. Their properties are high Q factor, very low SRF, higher inductance values that goes up to 47 microhenries. The tolerance is 5%, and they are available in four sizes of 402 or 603, 0805 and 1008. These inductors are widely used in radio frequency circuits due to their high inductance value, excellent EMI separation, and ability to operate at lower frequencies if we compare to air core or ceramic core inductors. Their core has higher permeability, provides great inductance in small sizes. Good EMI suppression that reduces unwanted noises, works well at RF frequencies used in megahertz to low gigahertz applications. Then comes WE-RFH. It has the larger current carrying capacities than WE-RFI. It also comes with high quality factor, high thermal stability, inductance that goes from 0.47 microhenries to 10 microhenries. Inductance tolerance comes with plus minus 5%, and the only size available in this series is 1008. Then comes the air core inductors. Air core, as we say, air core, so it comes with air as in core, there's no core. So it's a thick winding copper wire in a spiral shape. Properties, extremely high quality factor, because we are talking about air, so there are no core losses in these inductors. Very low RDC, very large current they can support, comes with a tolerance of 2% and 5%. We offer many different sizes in these coils, for example 1322, 5910, 4248, etc. Then what are the benefits of this air core? No core saturation, obviously, high efficiency and high frequency, high Q factor, in fact the highest Q factor in all the series, temperature stability, but it comes with some disadvantages, larger physical size, lower inductance per volume, and it is the main applications where it is used is broadband IO filtering, frequency selection, and impedance matching. Then comes the last WE-ACHCs, high current air coil inductors. These inductors comes with a flat wire for high current and high frequency applications. They can support extremely large currents up to 40 amps. None of other inductors can do that. None of other RF inductors can do that. Extremely high Q, very low RDC, comes with a tolerance of 20%. The two sizes available are 1010, 1212. Applications, high power filter, high current applications, and RF voltage regulator in RMI, etc. Then comes the multilayer ceramic inductors. It is formed by layering the ceramic materials and a coil conductor to create an integrated monolithic type inductor. What are its properties? High RDC, low Q, high SRF, double side polarity marking, comes with a tolerance of 2 and 5%, and many different sizes are available in this series as well. Now, the SRF trade-off wire wound versus multilayer inductors. Usually, the wire wound inductors have lower self-resonant frequency when we compare to multilayer inductors. Why is it so? Because the SRF of an inductor is heavily influenced by its construction. Wire wound inductors are made by winding the wire, and in those windings exists the parasitic capacitance. This capacitance reduces the self-resonant frequency of the wire wound inductors. In multilayer ceramic inductors, it's low because the ceramic layers in that act as dielectric, which reduce the capacitive coupling between the layers. That is why if we are choosing an inductor for high SRF, multilayer are the best choice. Then comes the TCI. It is formed by the photolithographic process. The properties are inductance values comes from 1 to 27 nanohenries. High precision, extremely thin, low inductance values, high SRF, comes in two sizes, O201 and O402. Now, a quick overview. Air core inductors, high Q, no core losses, suitable for high frequencies. Ceramic, high Q, stable performance used in RF filters. Then ferrite core, higher inductance, a small size, but with core losses at high frequencies. Multilayer inductors, compact, SMD friendly, but lower Q factor than wire wound. Now, what are the fundamental roles of an RF inductor? It is more than just a coil. So, the inductors are used in impedance matching for maximizing the power transfer between the circuit stages, for say between an amplifier and an antenna. It is used in filtering, blocking the unwanted frequencies in LC tanks, band pass or band stop filters. Then other application is biasing and choking, allowing DC current to pass while blocking RF signals. Then comes the resonance, forming tuned circuits with capacitors for oscillators and filters. Now let's see what are the emerging trends in this RF inductor field. First, miniaturization. As we all see in electronics, everything is going towards miniaturization, so do the RF inductors. So demand for the smaller packages for 5mm wave modules, wearables and IoT devices. Second, higher frequency support. Components designed for greater than 6 GHz supporting 5G, Wi-Fi 6E are in demand. Advanced materials, use of low losses, low permittivity ceramic materials to boost high Q. For most of the application, we require quality factor as high as possible. Embedded components, inductors, fabricated directly into the PCB substrate for reduced size and improved parasitics. Automated tuning, AI and ML, so it comes here as well. Drive the system for most real-world tuning of the matching networks using tunable inductors. Now, the key design challenges that engineers face with these coming trends. The Q factor trade-off. Achieving high Q factor in ultra-miniaturized package is extremely difficult. Parasitics are paramount, they govern the system performance and it's very difficult to tackle with them. Current handling in small sizes, preventing saturation in power dense design is a major challenge. Modeling accuracy, simulation models must be exceptionally accurate to predict performance at high frequencies. Then manufacturing variability, tighter tolerance are harder to achieve with smaller components impacted the yield and performance consistency. Now, the conclusion and the key takeaways. So, I'd say RF inductor is a critical component that are indispensable for impedance matching, filtering, biasing in the wireless systems. SRF and Q factor are the king. Always operate below the SRF and strive for the highest quality factor at your target frequency. Then, selection is the balancing art. It always requires juggling between electrical specs like inductance, quality factor and SRF, physical size along with cost. Trend points to miniaturization and higher frequencies. So, designers must adapt to the smaller components. The challenges are significant: overcoming parasites, losses, skin effects, modeling complexities is the key to successful high-frequency design. Now, for further information, you can go to our website where we have some very detailed application notes for RF inductors. You can find it directly on our website. And you can also go to the Red Expert and find our S-parameter models of all the inductors in there. So that wraps up my presentation here. Thank you for your time and attention. Now I'd be happy to answer any question that you may have.
So, yeah, thank you, Anhuba, for your interesting presentation. Now we'll come to your questions. Before we start with the Q&A session, I will share the handout from the presentation from Anhuba, and then everybody can download it. Okay. So now you can download it. This was the also the first question in the chat that I see. Yeah, now this was already answered. Okay, then I would say we can start with the first question. It was this one. Is there a specific reason polarity is marked on VMK inductors?
Yes, that's a good question. For sure, there's a significant reason why the WEMK, the multilayer inductors, comes with a polarity marking. Since the internal structure of these inductors is not perfectly symmetrical, the value of inductance varies little bit depending on which side we are placing the inductance. So in order to achieve tighter tolerance, it becomes very significant to add the marking which signifies the starting point of the geometry inside. And the second reason is that due to mutual coupling, inductors which are very close to each other, if the inductors are very close, there will always be some mutual coupling. However, if the inductors are kept in the same orientation, the coupling will be lower. So the conclusion is, on one side, if marking allows us to have tighter tolerance, other side, it allows the customer to place the component very close to each other.
Okay, thank you for the answer. Then I would say go directly to the next question. This one, I would say, in an impedance matching network, if I'm unable to get a good match, how can I determine if the problem is due to an incorrect inductor value, a low quality inductor, or something else entirely. Yeah.
Okay, so a bad matching can be because of several factors. So what we do is first just recalibrate the VNA and check out for any fixture errors. Then swap the inductors, check with an inductor which has a very good quality factor. And if you are able to recover the match, then it's obviously the inductor that was causing the error. If not, then just extract the impedance from the S parameter and check whether the reactance was inductive or capacitive, and check for the ground return or nearby coupling. These are the steps that I would do in the beginning.
Okay, thank you. Then next question. Yeah, let's do this one. Is it okay? Live?
Yeah.
Yeah. Can we achieve high inductance values with air core?
Sure, we can achieve high inductance values with the air core inductors, but since there's no core, so we'll have to make many number of turns to achieve high inductor values, which comes at a cost of size. So if your design can accumulate a bigger inductor or size is not a constraint for you, we can surely achieve high inductance value with the air core inductor.
Thank you. Then next question. Say this. Yeah. Okay. How does the plating material, gold or tin, impact the performance of ceramic inductors?
That's a good question. RWE-KI series, the ceramic inductor, comes with a gold plating, and that is for a reason. One, this gold plating gives better corrosion resistance, so you will not face any corrosion or oxidation in your parts. I would say tin plating is cheaper, but it comes with higher losses and is prone to oxidation. So the choice is trade-off. Use gold for high performance and reliability, and tin for cost and performance. So if you have an application for mass-produced devices, just like smartphones, you can use the tin plating inductors. But if your application demands higher reliability, then the gold plating ones are the choice.
Okay, thank you. Then I would say we are finished for today. Anhuba, thank you for your interesting presentation and for the answers. Thank you for joining. Thank you for your attention. Yeah, we had a lot of other sessions of this week during the Digital WE days. Yeah, we just don't know. Hopefully you see us on our next session, and yeah, stay tuned and bye-bye.